everyone. Today we are going to introduce the concept of complex numbers, which can be referenced in Section 9 of Chapter 5 from our textbook. So open your notebooks to a new page, and here we go. Let's recall the concept of square root. Now when we evaluate the square root of 4, we say that its square root is 2 because 2 times 2 is equal to 4. Now, in the past, we've said that the square root of -4 cannot be simplified, since there are no two real numbers such that something times itself would yield -4. But mathematicians back in the day wanted to create a placeholder to make some progress in some of our equations. So what we use as a placeholder for this idea of taking a square root of a negative is to call this guy, the square root of -1, imaginary I. From now on, when we simplify any type of a radical expression involving the square root of a negative, we want to replace that square root of -1 with the imaginary unit, I. So from now on, that's how we'll refer to the imaginary unit, I. Pure imaginary numbers are any type of a number that has a factor of I in it. So for example, I could have a number called 2I, where I is treated as a variable, but we know that its value is equivalent to the square root of -1. I could also have -2I. I could also have a radical expression involving I. For example, I times the square root of 2. Again, with these three examples, I is treated as a variable in computation, but we know that it's just a placeholder for the square root of -1. So let's consider some other things that happen with this idea of I being equal to the square root of -1. If I wanted to evaluate expressions involving other negatives, I have to be careful by analyzing the equivalent expressions. So, for example, what would happen if I were to square both sides of this expression? So, I'm going to raise both sides to the second power. That means that this is equivalent to I squared equals -1. Now that's kind of funky. We actually end up with a real number as a result of squaring an imaginary number. This is where it's useful to have this I as a placeholder so that we can actually make some progress in some of our expressions that involve the square root of a negative. Now, what if I take that original expression, I equal to the square root of -1, and I raise both sides to the third power? What I would then want to do is use my exponent rules to separate this idea of the square root of -1. Instead of raised to the 3, I'm going to separate it into the exponent of a 2 times the square root of -1 raised to the 1. Again, this is an exponent property. When you're multiplying like bases, you can add the exponents. So I'm separating my square root of -1 raised to the third power into a factor of the square root of -1 raised to the 2 and the square root of -1 raised to the 1. Since we know that the square root of negative 1 squared is equal to negative 1, I now have that I cubed is equal to negative 1 times the square root of negative 1. And since we have the defined imaginary unit to be equivalent to the square root of negative 1, I get negative 1 times I, which is simply negative I. So from here on, let's just memorize that I cubed is equal to negative I. Now let's analyze what happens when I raise both sides to the fourth power. So if I'm given I equals the square root of negative 1 and raise both sides to the fourth power, let's consider what we've done in the previous examples for powers of I. So we know that the square root of negative 1 raised to the 2 is equal to negative 1. I'm going to separate my expression, the square root of negative 1 raised to the fourth, into this square root of negative 1 raised to the 2, again, times the square root of negative 1 raised to the 2. Because I know that the square root of negative 1 squared is equal to negative 1, and I know that the square root of negative 1 squared is equal to negative 1 again. When I multiply negative 1 to negative 1, I get a product of positive 1. Now, the reason why we are nitpicking this concept is because we are starting with the concept of I equal to the square root of negative 1. And we have to be careful because not all of our rules that apply to real numbers will apply in this case. However, since we know the square root of negative 1 squared is equal to negative 1, we can manipulate our expression. So far, we have analyzed powers of I with an exponent of 1 through 4. So let's review those. If I have I to the 1, by definition, we know that's equal to the square root of negative 1. So from now on, if you have I to the 1, let's just write it as I. That's our placeholder for the square root of negative 1. We evaluated previously that I squared is equal to negative 1. I cubed is equal to negative I. And I to the fourth is equal to positive 1. Let's see what happens when I raise I to the fifth power. So here's our imaginary unit, I equals the square root of negative 1. Raising both sides to the fifth power, let's build upon the previous examples that we've already done. We know that I to the fourth is defined as 1, so let's separate this exponent of a 5 into an exponent of a 4 and an exponent of a 1. Again, we know that the square root of negative 1 raised to the fourth power can now be substituted with the value of 1, and we already said that the square root of negative 1 will be replaced with I. So this should seem familiar. We've evaluated the power of I to the 1 to be I, and this is the same thing. I to the fifth is now I. So as you can imagine, we're going to repeat this pattern. So we only have 4 distinct powers of I. So let's refer to the list of the powers of I that we already have in our notes. We have that I to the first will just be written as I to the second will be written and simplified as -1, I to the third is equivalent to -I, and I to the fourth is equivalent to 1. Since we just simplified I to the fifth to be equivalent to I, as you can imagine, the pattern repeats. I to the sixth is equivalent to I squared, which is -1. I to the seventh is equivalent to I cubed, which will be simplified to -I. And I to the eighth, and any exponent whose multiple or whose exponent is a multiple of 4 can be simplified as 1. So it's a good idea from this point on to memorize this chart. Let's memorize that I to the first power will simplify to I and is defined as the value of the square root of -1. I squared is equal to -1. I cubed is equal to -I, and I to the fourth is equal to 1. So make sure you memorize this. Let's simplify a few examples. Say I had I raised to the 46. Our goal is to simplify this by manipulating our exponent. We have an even exponent here. So let's simplify this power of I. We know that it's equivalent to either I, -1, -I, or +1. Since my exponent is even, however, not divisible by 4, I'm going to separate this into I squared times I to the 44. I've done this because I know that any exponent that is divisible by 4 can be substituted for the value of 1, and I squared is equal to -1. Therefore, I to the 46 is equivalent to -1. This is by using logic. Now, if we want to, we can memorize our chart of our powers of I and simply take our exponent, divide it by 4, and see what our remainder is. 46 divided by 4 is equivalent to, well, since 4 goes into 4 one time, and 4 goes into 6 one time without going over, with a remainder of 2, we now know that I to the 46 will be equivalent to, let's refer back to our powers of I chart. Here is our powers of I chart. Again, we know that I to the 46 is equivalent to I squared since 2 is our remainder when we divide 46 by 4. Likewise, any exponent divisible by 4 will yield I to the 1 if our remainder is 1, I to the 2 if our remainder is 2, I to the 3 if our remainder is 3, and I to the 4th if our remainder is 0, since it would be evenly divisible by 4. Again, to reinforce this concept, let's see what happens when we simplify I to the 81. Using our memorizing method, let's divide 81 by 4, and we know that 4 goes into 81 evenly 20 times with a remainder of 1. Again, let's refer to our I chart. Since 81 divided by 4 gives us a remainder of 1, I to the 81 will be equivalent to I. Now let's simplify an expression equivalent to the square root of negative 2 times the square root of negative 3. Now we have to be careful here, since our product property of the square root of a times the square root of b equals the square root of a times b only applies to values of a and b such that they're positive. So we can't simply use this property to simplify the square root of negative 2 times the square root of negative 3. What we need to do is utilize our definition of an imaginary number. So I'm going to think of the square root of negative 2 as the square root of negative 1 times 2 times the square root of negative 1 times 3. I now know that the imaginary unit is defined as the square root of negative 1. So I'm going to simplify the square root of negative 1 times 2 as I times the square root of 2 times I again times the square root of 3. Notice that I have two I factors here. I'm going to combine those two by multiplication, which is equal to I squared. And now I can use my product property of two radicals right here, since a, in this case, is equal to 2 and b is equal to 3. Both are positive values, therefore the product property is valid. So I'm going to simplify this in finale by saying that I've got I squared times the square root of 6 and the square root, I squared is equivalent to negative 1. Now let's solve an equation given by 2x squared minus 32 equals 0. Now if I want to solve, I want to isolate my variable. So let's add 32 to both sides, and we end up with 2x squared equals positive 32, and then divide both sides by 2, and we end up with x squared equals 16. Now when we are asked to solve an equation, we want to find all possible solutions. So when solving for x in this case, we want to take the square root of both sides, but keep in mind, we have two solutions that would make this true. We know that the square root of 16 is 4. However, when I take the square root of both sides and I'm solving for x, we want to make sure that we know that x is going to be equal to plus or minus the square root of 16. Since both the positive and the negative square root will make this true. And we can even check by plugging it in. Notice that if I plug in a negative 4 into my variable x, the negative would be squared, which would make it a positive 16, and the positive 4 still makes it a 16. So when solving for a variable and taking the square root of both sides, let's make sure that we use both solutions, the positive and the negative square root. Now let's solve this equation. Say I have 3x squared plus 27 equals 0. Solving for x, we want to isolate the term that involves our variable. By subtracting 27 from both sides, and then dividing both sides by 3, I end up with x squared is equal to negative 9. Now in the past, we would say that there is no solution. But now, we have access to this new concept of an imaginary number. So, if I were to solve for x, I'm going to take the square root of both sides. But let's remember, when I take the square root of both sides when solving an equation, both the positive and the negative square root will be solutions. Now we have to simplify the radical expression that we get as a result. The square root of negative 9 is going to be equal to, taking into account that negative 9 is the same thing as negative 1 times 9, we want to recognize that the square root of negative 1 is equal to I, and the square root of 9 is equal to 3. In simplified form, it really makes more sense to write our answer as 3i. Typically, we'll have our integer component in front of the imaginary unit, sort of like a coefficient of a variable. So there's our solution, and we can even check. When I plug a positive 3i in for the value of x in my equation, I end up with 9 times 3 to be 27, and I squared is equal to negative 1. So let's check this on the next page. To help reinforce the concept of imaginary numbers, let's check our solutions in this equation. So here I have 3 times positive 3i, all squared, plus 27. We're verifying whether or not this is in fact equal to 0. Now, we know that 3i squared will be equivalent to 9i squared plus the 27. Again, verifying if this is equal to 0. Since I squared is equal to negative 1, we now can see that negative 27 plus 27 is certainly equal to 0. The same thing will hold true if I plug a negative 3i in. So now that I have a negative 3i in for x, I have negative 3 times negative 3, which is positive 9, times I squared plus 27. Again, we're verifying if, in fact, this is equal to 0. So 3 times 9 is 27, and I squared is equal to negative 1. So negative 1 times the 27 is equal to negative 27 plus the 27, again, certainly equal to 0. Therefore, both positive and negative 3i are solutions to our statement 3x squared plus 27 equals 0.
Made with Doodlecast Pro.